I'm Lichen. Zhang from MIT. Today I'm going to talk about convex optimization with integer minima in nearly quadruple time. This is a joint work with Haotian Jiang from MSR, Li from MSR and the University of Washington, and Zhao from Adobe Research. So let's start with some background on convex optimization. Suppose you're given a convex function f from Rn to R, and you do not directly have access to this function. Rather, you access it via a separation oracle. The separation oracle functions as follows. You feed it into a point x in Rn if it is a minimizer. The oracle returns yes, otherwise it returns a hyperplane that separates x and the minimizer. So a popular choice, you might imagine, would be the gradient of your current point x. If it's the minimizer, you know the gradient is zero. Otherwise, by the property of convex functions, it self operates as a separating hyperplanes to the minimizer. So the goal is, of course, minimize the convex function. We are using as few as cost to the separation oracles and additional arithmetic operations. So to talk about our work, we need to talk about something called strongly polynomial time. We see a convex optimization algorithm runs in strongly polynomial time if its runtime does not depend on the size of the problem. What does that mean? So the size can be the range of the function. For example, the largest value your fx can be, the Lipschitzness, the condition number, length of the binary representation, etc. So this, as we will see later, obtain an algorithm for convex optimization with strongly polynomial runtime is essential for many applications. However, without any structural assumptions on f, the problem is not easy. For example, it is still a major open problem whether one can solve the linear program in strongly polynomial time. On the other hand, there exists a class of somewhat easier problem that admits strongly polynomial time algorithms. So one example is a submodular function minimization. Given an element ground set V, the function f is a mapping from any subset over the set V to a real number. And we say the function f is submodular if it admits this marginal cost property, in the sense that suppose you have two sets x and y, x is subset of y, and you add an arbitrary element that is outside of y, then the function value increase of f of x union this new element is greater than f of y union this new element. And so we assume that we have direct access to the evaluation oracle of this function, in the sense that given any subset x, it returns us the value of fx. So what does strongly polynomial time means in this scenario? It means that the runtime of our algorithm does not depend on the largest value of f, which is captured by the infinity norm here, essentially the maximum over all the subset x of fx. And then there is a long line of very successful works on obtaining a strongly polynomial time algorithm for SFM. So, given the success of strongly polynomial time SFM, it is natural to think, what can we generalize from this case? So for submodular function minimization, we note that all the extreme points of function f are integral. So one natural question to ask is, suppose we assume all the extreme points of f are integral, can we develop a strongly polynomial time algorithm for it? And an additional assumption we may impose here is the minimizers of f have a infinity norm bounded by R. And this R can be as large as 2 to the poly n. There exist prior works due to Jiang that shows that this is indeed possible. And he shows that, in fact, one can obtain an algorithm has a subquadratic dependence on the number of calls to the separation oracles. And the downside of his algorithm is it requires a lot of additional arithmetic operations, namely at least in the order of n to the eighth power. So from an oracle call perspective, this is an amazing algorithm. Subquadratic is highly non-trivial, and as we will see later, this extends to a subcubic oracle call algorithms for SFM. However, if one considers the number of arithmetic operations, this algorithm is not super practical in the sense that it takes a super long time to run. So um, what can we do better here? So our perspective is that subquadratic oracle calls is very nice, but it comes at a very high price on the number of our additional arithmetic operations. Can we slightly sacrifice the number of oracle calls in exchange of faster algorithms? So this precludes our main result of this paper. Given a convex function f with all the extreme points integral and containing a box of radius r, then we develop an algorithm that minimizes f using n squared times log n r oracle cost to separation oracle and using only n to the fourth power to log n r additional arithmetic operations. Note that the number of oracle calls are slightly worse than the result by Zhang earlier, but we obtain a much improved additional runtime. And then one of the important implications of our algorithm is a strongly polynomial time algorithm for some modular function minimization. So one can directly apply our method to the so-called Lovat's extension of SFM. And as a corollary, we obtain an algorithm that uses only n cube log n oracle calls, evaluation cost to the evaluation oracle, and n to the fourth power times log n additional arithmetic operations. So prior works either due to Jiang, which obtains a subcubic oracle calls, but n to the eighth power additional runtime, or another line of work that uses a different approach, obtains n to n cubed times log square n oracle cost and n to the fourth times polylog n additional runtime. We strictly improve all aspects of the second line of works, and compared to John's work, we significantly improve the additional runtime. So let's dive into the algorithmic details of our method. So let's start by reviewing the work of Zhang. So his algorithm basically works as follows. So we start by maintaining a polytope k and the integer lattice lambda. So the key invariants that are maintained across the algorithm is we want the polytope always captures the minimizer, and the minimizer always lies in the lattice. So we kind of need to update the polytope and the lattice simultaneously in a fashion to maintain this invariant. So the first step is to find an ellipsoidal approximation to the polytope k, because any kind of optimization on the polytope directly is not easy, but on ellipsoid much easier. So John's method is say that we find the center of gravity and the covariance matrix of k, then we consider the ellipsoid induced by this by the center of gravity plus the covariance, and then it subsequently utilizes this integer lattice to find the shortest vector over the ellipsoidal local norm, meaning that the norm is related uh, by the covariance matrix. The key intuition of his algorithm is that when the shortest vector is relatively long, then we can keep shrinking the ellipsoid by doing cutting plane steps. On the other hand, if one shrinks the volume, the shortest vector becomes smaller. And when the shortest vector is small enough, we can no longer make progress by shrinking the volume. And what we do is we're projecting onto the orthogonal complement of the shortest vector. We reduce the dimension of subspace by 1, and we recurse the algorithm. From a computational perspective, there are several bottlenecks of his algorithm. For example, computing shortest vector approximately is very costly. And to ensure each of his cutting plane steps to guarantee reduced volume, he utilizes a less efficient method of the cutting plane method due to Bertmus and Wampela. So to make it more concrete, say we make T oracle calls. So his algorithm needs to call the shortest vector and the cutting plane for T times. For the shortest vector, it's roughly n to the 4th power time, and for the cutting plane, it's in the order of n to the 6th power. Even though your T can be subquadratic, this still leads to, because you have additional log factors in this algorithm, this still leads to n to the 8th power operations algorithm. How do one achieve a speed up given this framework? So if one executes the cutting plane steps in blocks of size n log n, then there exists faster variants of idea. And the total runtime is much faster due to Zhang, Li, Song, and Wang. The runtime can be lowered to n cubed times log n. However, if you use the YDS cutting plane method, the volume drop is only guaranteed after O of n log n steps. This means that we can only measure the length of shortest vector after O of n log n steps of cutting planes. So, of course, we will see later this comes as a price of a worse oracle cost. But the nice thing here is we only need to perform the shortest vector approximation after n log n steps of cutting planes. So this gives us some leeway to use some faster shortest vector approximation algorithms because now the number of calls to shortest vector is smaller. And we will see how this will lead to an algorithm with additional arithmetic operations counts up to O of n to 4th power times log n r. Since we are lazy in computing the shortest vector, it is possible that when we need to projecting the problem onto a smaller dimension, we miss this opportunity because we are still working on cutting plane method. And this comes at the cost of a worse number of oracle costs. But we will show that this is not too bad. And actually n squared times log n oracle cost suffice. So let's try to dive into more details of the algorithm. So YDS cutting plane algorithm differs from the center of gravity plus covariance method in the following sense. Suppose I give you a polytope K parameterized by a matrix A of size m by n and a vector B. Then we can write down the Hessian of the so-called log barrier of this polytope, and the Hessian is defined as follows. So essentially, it's a sum of outer products of the constraints AI of the hyperplanes AIs related by the square of the slacks. And YDR basically says that if you look at this Hessian matrix HX, it naturally induces an ellipsoid. I can consequentially define a function that measures the volume of this ellipsoid. And his idea is we can use the minimizer of this function as a center, denoted by the volumetric center VC of K, and we use the H applied to this point as its covariance matrix to develop an ellipsoid. And so the idea is instead of the standard center of gravity and covariance. This also produces a so-called Dicking ellipsoid. And the Dicking ellipsoid sandwiches the polytopes while preserving the minimizers from the volumetric function. So why they are trying to do this kind of algorithms? The key idea is a scared version of this function f is a so-called self-concordant barrier function for k. Therefore, you have this very natural sandwiching condition between the point of k and the ellipsoid induced by the by centering at the volumetric center of k and the Hessian of the volumetric function. But recall, in our algorithm, we do not have access to the Hessian. Instead, we compute the h function applied to the point we say of k. So we have to show that it is actually fine that you do this replacement. So for the left replacement, it's actually quite straightforward because one can show that if you use h as your covariance, you always have this left containment. So the harder part is to show that for the right hand side, for the outer ellipsoid, it still contains the polytope. So we provide a characterization of the ellipsoid induced by h of k centered at the volumetric center. A key property to leverage here is that h of k and the Hessian of a volumetric function are spectral approximation to each other. Therefore, one can conclude a one-sided containment that encloses the ellipsoid induced by the Hessian with the ellipsoid induced by the H function by a melody blow up on a number of constraints. And we can use this sandwich to show that so as a consequence, we have shown that you can use the ellipsoid induced by the volumetric center plus the h function to sandwich the polytope k, and use this sandwich condition, we can further show that this H matrix is a good spectral approximation to the covariance matrix. So once settled down on the ellipsoid, we need to examine the center of this ellipsoid. I kind of lied to you in the sense that I say you only need to show that the sandwiching holds by considering ellipsoid centered at the volumetric center. But as you can see, the volumetric center is a minimizer of another convex function, so finding it exactly is not time efficient. Instead, we compute approximation of it using Newton's method. And by Vaidya, he shows that Newton's method can be implemented very fast. So we prove that this approximation actually suffices in the sense that suppose the approximate center has a very small, very close to the volumetric center in the sense of function value, then the H matrix induces by these 2 points a good spectral approximation to each other. And further, the 2 points are close in the H norm. Therefore, it is safe to replace the volumetric center by this approximate center C. It remains to bound the number of oracle calls. So the key here is potential function introduced by Zhang. It is a log of the volume of the polytope and the determinant of the lattice, in the sense that it simultaneously captures the volume change of these two objects. And recall that our algorithm essentially says that computing on the polytope is expensive, so we use an ellipsoid. So when using this ellipsoid to approximate k, we use this outer ellipsoid approximation, and this will inevitably blows up the volume by a factor of n to the O of n, which will play a part in the later bound on the oracle cost. So the key argument here is after k times of collapsing the dimension because each time we use this outer ellipsoid to approximate, the volume blows up by a factor of n to the O of nk. And one can prove using some extra structural conditions on the lattice and dual lattice that if we take the exponential of the potential under k plus 1's iteration is smaller than or equal to the exponential of the potential initial potential times the extra factors. Let us try to parse the factors here. So n to the O of nk is due to the ellipsoid approximation. K to the O of k is due to the volume blows up after we slice a dimension, projecting onto a smaller dimensional space, and n to the O of k is essentially the price we're paying to use the h of z to approximate the covariance matrix. And finally, we have this factor lambda 1 to the k. This lambda 1 is the length of the shortest vector over the lattice lambda 0 under the hk0 inverse norm. So all the pieces here have been provided to us. It remains to get a good handle on this length of the shortest vector. So to bound this quantity, recall that we use approximate shortest vector algorithm, and let gamma denote this approximation ratio. And setting, if we set if you recall the algorithm works as if the length of shortest vector is large, I do cut and plane. If it's small, I collapse the dimension. If we set the threshold properly, then we can show that the length of the shortest vector is at least a constant over gamma times n to the n, and put it together, we have this nice bound on the potentials. And recall that the dimension is inherently n-dimensional, so we can at most collapse dimension for n minus 1 time, and we set k as n minus 1 and take a log. We get a bound on the number of oracle calls, which is n squared times log n plus n to the n times log gamma n plus n to log r. So how do we interpret this bound? So n to log r is the initial potential because if you set the initial object, initial k, and the lambda property, you just naturally get this. And what is the gamma here? The gamma here comes from the approximation ratio of the shortest vector. And here for us, the gamma is 2 to the n because we use a faster shortest vector algorithm. And if you look at this bound, you might be wondering that it seems for the initial Zhang's algorithm, he also has this n to the n times log gamma n factor, n times log r factor. So where do the extra logs come from, and are they actually necessary in our algorithm? So there are several reasons why, in terms of log factors, we are worse. So for the first one, in Zhang's algorithm, because he does not care too much about the uh, additional runtime, he uses a relatively slow algorithm to compute approximate shortest vector, but it provides him a sub-exponential dependence on the approximation ratio gamma. So this is one of the reasons he can avoid the gamma to be 2 to the n in the second part of the oracle cost. And then moreover, the first part, the n squared times log n part of our algorithm, basically comes from we use many fast ellipsoidal approximations to get a very fast algorithm. So this inevitably blows up the volume by a factor of n to the O of n, and if you take log, this is n log n. So in contrast, Zhang develops a very sophisticated schemes to carefully control these ellipsoidal blowups and shave off the extra volume increment due to them. However, from a runtime perspective, this is not exactly the best thing to do, as it make the overall algorithm even slower. It is therefore unclear to us that whether you can remove the quadratic barriers while maintaining a relatively good runtime. So to summarize, we present an algorithm that minimizes the convex function with integral extreme points of radius r, and it uses n squared times log n oracle cost to the separation oracle, and additional n to the fourth power times log n arithmetic operations. As a consequence, this leads to an algorithm for submodular function minimization, uses n cubed log n cost to evaluation oracles, and additional n to the fourth power times log n arithmetic operations. Some future directions of our work, including improve the approximate shortest vector approximation ratios. Suppose we can get a sub-exponential approximation ratio while still maintaining a relatively good runtime. This will necessarily remove one obstacle of improving the number of oracle calls of our algorithm. And consequentially, one might wonder whether those careful, those ellipsoidal approximation maneuver can be further improved. Like one can further control the volume blow up while develop a relatively faster scheme to do all these operations. And that's all. Thank you.